Hello class, this is CSE-5720, Section 2, Week 7, Fall 2025. Right, to catch us up back to speed from last week's video, let's remind ourselves with what referential integrity is, and it's a constraint that says if we are referencing something and we try to add something to the database that references that thing, we can only add it if it exists. So we can only add class sections if the relevant course already exists. We can only add courses if the relevant department already exists, and we can only add instructors if the relevant department also exists. Without those, these are specifically foreign key constraints, and without them, we can just add willy-nilly any courses and instructors we want for non-existent departments and non-existent courses. Right before we continued off with what happens if we try to update something that has a foreign key constraint, right before we were to discuss that, we also updated the following schemas so that they have check clauses that ensures for section that our course takes place in fall, winter, spring, or summer, that our section takes place in fall, winter, spring, or summer, that our course is at least 1 or more credits, and that our instructor has a minimum salary, and that our department budgets are greater than 0. By default, a foreign key references the attributes of the reference table's primary key, though there is a shorthand that we can also use. So where we had left off last video is what happens if you do an update that violates a referential integrity constraint. Well, the normal course of action is to just reject that action. But what happens if we try to delete or update something? So here is the section and classroom table declarations. So, foreign key building room references classroom. So, section and classroom, we can only add a section if the relevant classroom exists. But what happens if we update the classroom table and oops, now the room doesn't exist anymore? Say in our university example, we did a remodeling, and now what used to be backroom 103 is now backroom 1005, and what used to be backroom 118 no longer exists. So here is a table of sections, and they were to take place in the newly remodeled backroom building, and now backroom 103 no longer exists. Now what? So what used to be room 103 is now room 1005. Well, the most reasonable thing to do is to just update the room number, which is exactly what onUpdate Cascade does. If we did instead onDelete Cascade, it does something similar. So you'll notice that we used to have a room 118 in our back room building, and it's gone. And we have a class that references that non-existent building. So what happens now is that course also gets deleted. That's a bit draconian, and it might be reasonable to think that this is a rather draconian action. After all, it's not uncommon to have fields in a university's course offerings to be determined. For example, they have yet to find an appropriate classroom or an appropriate time slot or an instructor to even teach the course. So if for our university example, it's more reasonable to not delete the course, but rather just change it to something else in the meantime, such as change it to TBD, to be determined, then what we could do is not delete the course, but rather change it to some other value. For example, we could just change it to null, but only if we are allowed to have null values for room number and capacity. But deeper than that, it also depends on whether it makes sense for a class section to exist without a classroom. For our purposes, we're gonna say it does. It does make sense for a classroom. It does make sense for a class section to exist without a classroom. But only if you can find a classroom for it right before the semester starts. So, if we can have null values for building and room number, we can have, instead of onDelete the cascade, onDelete set null. If we want to set it to some default value, like to be determined, or I guess default building, instead of onDelete cascade, it's onDelete set default. So for completeness, here is a listing on what every possible onDelete clause does. So onDelete cascade, if you delete a classroom, any sections that reference it are also deleted. OnDelete set null, if you delete a classroom, any sections that reference it have building and room number set to null, which only works if those attributes can be null. OnDelete set default, if you delete a classroom, any sections that reference that classroom have building and room number set back to default values as defined in the classroom relation. And onDelete no action, that's the default behavior. You're just prevented from deleting the classroom altogether. On update cascade, if you update a classroom, any class sections that reference it are also updated. On update set null, if you update a classroom, any sections that reference it have building and room numbers set to null. On update set default, if you update a classroom, that should say update, not delete. If you update a classroom, any class sections that reference it have building and room numbers set back to default values. And on update no action, that is the default behavior. The DBMS will just prevent you from updating the classroom. Sometimes when you have a chain of updates and deletes, no, let me go back. Sometimes when you do an update or delete this way, it can trigger a chain of updates. It's also possible that this chain can lead to a referential integrity violation. We can't update it anymore because we've already violated referential integrity, so the system aborts the entire transaction and it performs a rollback instead. But it's also possible that if we just kept going, even with those integrity constraints violated, we could just keep going and then find ourselves with that violation totally resolved, which can only happen if you defer constraint checking. Instead of checking it after each operation we do, we just check it. We just don't check it right away, we check it at a later step. But the default behavior of SQL is to check constraints immediately. Deferring constraint checking isn't supported in most implementations, but there are workarounds to get around that as well. Alright, so this is going to be the last section in 4.4.7 before I talk about the homework 1 answers. So this is going to be a lot more complex because we're going to build an assertion from the ground up, and it is pretty complex. The SQL standard uses the check predicate clause, where the predicate can be an arbitrary predicate, and the predicate can also include a subquery. So here's an example. So, timeslot ID varchar 4, and I have a blank here. We can add a constraint to this table declaration. Check that the timeslot ID is in the timeslot relation. So specifically, it's added as part of the timeslot ID attribute declaration. So basically, what we can do is we can add a check clause for timeslot ID that says, okay, if we add this timeslot ID, we got to make sure it is in the table of timeslots. And that's the full check clause that we can just slot into this blank here. Check time slot ID in select time slot ID from time slot. So time slot is our table of time slots. What we're doing is making sure that we have a time slot ID that exists in our table of time slots. What this does is we can only add sections if their time slot IDs exist. So you can just add that in there. Another constraint we can add is this. Ensure each section is taught by at least one instructor. Sometimes you might have a class that's taught by more than one instructor. In other words, but in our case, we can only add sections if there's someone assigned to teach it, which we can add as another set of check conditions, but this would actually require several checks. Check course ID and select course ID from teachers. So checks like this help to ensure data integrity, but the more complex a check condition is, the more costly it becomes to test. Another way we can ensure our database another way you can ensure data integrity is to use an assertion. This is a predicate expressing a condition that the database should always satisfy. These are used for expressing integrity constraints that are too complex to express as domain constraints or referential integrity constraints. And here is the general format for creating an assertion. Create assertion name, check predicate. So here are these are some complex constraints that we would want our university example to uphold. An instructor cannot teach two classes within the same semester that have the same time slot, unless we are able to live stream the course into another classroom. That could happen, but for our purposes, we are assuming we can't do that. So that's one constraint we could also check. Make sure that an instructor is teaching two classes simultaneously. You might have similar checks at the student level. You cannot take two classes simultaneously. And you require special permission to even do that. Another constraint worth adding is a student's total credits must equal the total number of credits of every successfully passed class. Let's make an assertion based off that one. So, we want to calculate the total number of credits each student has, but it isn't enough to just reference the total credits from this table. We want more information from the takes relation and the course relation. So, say we have a student and we want to make sure that their total credits matches what it says in the student relation. So, what we can do is just look up a student's ID, look up every course that student has ever taken, look up the corresponding credits for each course they've ever taken, and assuming the student has passed those classes, we just add up all those credit totals up, compare it with the one in the student relation, and if the total credit matches the sum of the credit values of every course that student has ever successfully passed, then we know that that total credit is correct. This is where it's going to get deep. So, let's make an assertion based off of that, and it's going to take some time because we have to build it up from the ground up. So let's consider this query here. Select some credits from takes natural join course where student ID equals takes ID and grade is not null and grade is not F. So eventually we are going to make this query a part of another query. So this is going to be a subquery. But for now, what we can do is pretend that student.id equals takes.id instead says takes.id equals 00128. So we are going to check this for one student, even though eventually we're going to check this for every student. So let's consider how that query is performed. We do a natural join, as we normally would, and this is the table we get out of that. And then we evaluate the where clause, only consider rows whose ID matches the student ID of 00128, and rows where the grade is neither null or F. And then we evaluate the select clause, which says to just sum up everything in the credits column. Here we find that the student has 7 credits total. And there we go. We're not done yet because this query it's supposed to be part of a larger query, and this is the rest of that query. Select ID from student where total credit does not equal the subquery. So, we had assumed that our student ID was 00128, but stop pretending that because now we need to apply this to every student. So, let's add a few more students' total credits. So, here's a few more, and let's move these aside so we can bring back the student relation because that's needed in the from clause for this query. So select ID from student where total credit does not equal the subquery. We need this again. For ease of demonstration, we only need the first 3 students. Well, we're only going to consider the first 3 students. So we evaluate the where clause, students whose total credits does not match the result of the subquery, which is all of them. So the final thing to do is select the ID column. So now we have the result of this query in a query. Students whose total credit does not match the total credits of the classes they have successfully passed. As an aside, we can draw a few conclusions from this. Either a hacker came in and wiped out all the data, or these are transfer students, or not all information was successfully transferred, or this is probably the more logical conclusion. This is just a snapshot of the data, and we are only getting a small portion of the data because if we had all the data available to us, we literally would be here all night. Though, considering that our university database started off as a ad hoc system of programs and files, it's also reasonable that not everything was migrated to a SQL database. So let's finish everything up here. So we have the query that selects students whose total credits does not match the total credits of the classes they have passed. But we actually want this to be a part of our assertion. So our assertion was to make sure that no student exists such that their total credits does not match the total credits of all the classes they've ever passed. In other words, what we want is this table to be empty. So we need to take this query and stuff it inside of a not exists. So what we're doing now is making sure that no student exists whose total credits does not match the total credits of every class they've ever passed. So now we have this not exists clause, but we need that to be part of our check predicate condition. So now we're checking that there is no student whose total credits does not match the total credits of every class they have ever passed. But that's our entire assertion already. So we can just wrap that up with this create assertion statement here. So now, with a little bit of cleanup, we now have our entire assertion. A student's total credits must equal the total number of credits of every class successfully completed. So not all database implementations support check or create assertion. So a common workaround is to use triggers. And here's an example. We won't really be talking about triggers here, but it is further discussed in 5.3 if you want to look at it. And here is an example of such a trigger. So this trigger does the same thing as this assertion. So that's as far as I'm gonna go into chapter 4 right now, I figured I would just give you a little break, let you work on your homework and lab, which, oh, by the way, you do have another lab now. It's a bit shorter than the last one, and you should see the instructions on Canvas as well. But now, let's take this time to answer your homework 1 questions. So, okay, if you recall from homework 1, which was a while ago, you had the following questions. Number 1, construct an ER diagram for a car insurance company where you have the following entities and the following relationships. You also have optional features that you may also add, such as additional entities, additional attributes, and additional relationships. One relationship I decided to add into the answer key was one where a customer has a insurance policy. So that's something that we can add, and really I added it just to flesh out the entire schema so that everything is connected together. So that is number 1. Number 2, construct an ER diagram for a sports team. So you have players, matches, and teams. Optional information you would wish to include is a coach and a stadium. And relationships are which players play in which teams, and if you're including stadium, what matches were played at which stadiums, and if including coaches, which coaches coach which teams. I went as far as to include the coach and this relationship here, which coaches coach each team. So that's number 2. Number 3, you are to take one of those diagrams and turn it into a set of relation schemas. I'm going to show you how you would answer both questions and then turn how you would go about answering, converting both diagrams into a set of schemas. So here's the solution for number 1. So in class, I talked about this, but I had to make a few corrections. So I had vehicles involved as an attribute for accident, but after creating the involved in relationship, vehicles involved would just be the vehicle identification numbers. So that was an attribute that I just ended up removing altogether. Okay, but let's back up. We have the 4 entities here: customer, car, accident, and policy, with the following attributes here. I had to change customer as well. So instead of identifying customers by their policy number, they would be identified instead by their customer ID. So that's just an alternative to using policy number to identify customers. Also, it makes the relationship between customer and policy a lot more clear, in that we are identifying customers by ID and policies by policy number. And the relationship between those two is 1-to-1. A customer has one policy, and a policy is owned by one customer. We're not considering a customer having more than one policy or exchanging policies. We're just considering a simplified example of it's just one customer with one policy. So right there, we have 2 entities and 1 relationship already. I added this has relationship just for completeness. Again, it's just to make sure everything connects together in a more broader way. Even though I explicitly called for 3 relationships, I added a 4th one just to be more thorough. So really, this answer is contingent on whether you decided to add a relationship between customer and policy. Alright, so those are the customer and policy attributes. What about the car and accident? So a car is going to have the following attributes: make, model, year, and vehicle identification number. Technically, you can get away with only having the vehicle identification number, but it requires a bit of work to decode the vehicle identification number to get the make, model, and year, and it contains other information such as where in the world was this vehicle manufactured. And it also contains information such as the serial number, because it's a little bit hard to parse a vehicle ID number without a special tool or lookup table. We're going to add the make, model, and year, even though it's technically redundant, it's just easier to read. So we can identify a car uniquely by its vehicle identification number. What's also worth adding to this potential database is another attribute, license plate number. In that case, you would need either one thing or two things for that. And I guess it depends on how the database is going to represent data. Okay. So every US state has a different scheme for license plate numbers. In California, it is currently 1 number, 3 letters, and 3 numbers after that. At some point, they're going to run out and they're going to need a new scheme. But for now, that is the scheme for California. Other states have different schemes. So if we wanted to add license plate, and I'm just going to add this real quickly right here just to demonstrate. Do you want to include the state separately? Or do you want to add the state separately, or do you just want the plate number by itself? If you just want the plate number by itself, then that's really all you need, just the license plate. But if you also want to add the state, also what happens if you imported a different vehicle from outside the country, for example, then you have to generalize this to say state or country or whatever. My point is, do you want your license plate to include the state and plate number, or just the plate number by itself? Again, there are several different ways we can go about this. It would definitely be worth adding a license plate number to our table, because that's something that police could just look up for their purposes as well. Yep, I'm just going to leave it in there, even though it's going to push several things around if I did so. Alright, so now we have our car with the following attributes. I'll just take it out for now. Okay, an accident. A car accident is going to involve one or more cars. But it's also going to take place at a time and location, time and place. There are 2 ways we can go about the location, and that is using an address, or using a latitude and longitude, or using both. If we have a car accident that takes place in town, it would be perfectly reasonable to specify the location of the accident using an address. But if you have a car accident that takes place like outside of town, you might not have a reliable address, if at all. At that point, you might want to refer to the location of the accident by latitude and longitude. Or you might want to go with both. So, location is going to consist of two other attributes, address and latitude, longitude. This also depends on whether we also want to represent latitude and longitude as 2 separate attributes, or just a string that encodes information for both. I went with interpreting latitude and longitude as one string that encodes both, so we only have 2 attributes to worry about for location. For date, for completeness, we should also do this. Time, date, which would also include year, month, day, or whichever date format you're working with, and time would be broken up even further into hours, minutes, and I'm not sure if you need to be this precise with a car accident, but I guess with technology, being as advanced as it is, we might be able to get this precise. But I did not go this far with how you're supposed to specify time information in your ER diagram, so you could just leave it as date, or you might want to add the time anyway. Okay, so you have a location, you have a date, you have the cars involved. Now, in the diagram here, I had actually removed cars involved, and you'll see why in a little bit. Oh yeah, and I also added an accident ID, and that is because it's just easier to identify an accident by an accident ID. But if you don't have an accident ID, your alternative is to use both location and date as your primary key for your accident. And policy number, the primary key for that would just be the policy number. Pretty simple. So those are the 4 entities that we have: customer, car, accident, policy. So the relationships we have are owns. A customer owns 1 or more cars. So this would be a one-to-many relationship between customer and car. Involved in denotes a one. It's a many-to-one relationship between a car and an accident. But now that I think about it, could it actually be a many-to-many? Could a car be involved in more than one accident? Possibly. So this is just something that you might want to think about. So there are multiple ways to answer this question here. I'm just assuming that we have 1 or more cars involved in one accident. You might also notice that the diagram says 0 or more cars. And this is something I brought up in class. Does it make sense for a car accident to only involve 1 car? Yes, it does. That's when a car crashes into just a random object. We think of car crashes as involving at least 2 or more cars, but a car accident can involve just 1 car. It's just a car driving into a utility pole, for example. But can a car accident involve 0 cars? Can you even have an accident claim with no cars? Think about it. If you have a car accident with 0 cars involved, that's gonna be one of 2 things. 1, insurance fraud. Or 2, that's a test case for your database. So depending on whether you want to allow for fraud cases to be represented in your database, or even test cases to be involved in your database, you could either, so it depends on whether you want to allow for this. You can define a car accident as involving 1 or more cars or 0 or more cars. For the relationship ensures, this is a policy that ensures 1 or more cars. So this is a 1 policy to many cars, and has is a one-to-one or a relationship between a customer and a policy. So a customer has an insurance policy. I never explicitly told you to add this into your diagram, but I decided to add it just for completeness. Which is also why I had to swap out policy number for customer ID. That way, the relationship between customer and policy is a lot more neater, because the schema for that would need to require 2 unique IDs. So that's why I had to give customer their own unique ID, customer ID. That way the has relationship has the primary key of policy number and customer ID. Technically, you only need 1 attribute because this is one-to-one. We can identify a relationship using just one of the two attributes, but for completeness sake, I just showed both attributes. Because some of these are one-to-many, or many-to-one, or many-to-many, and in those cases, you need... In the case of many-to-many, you actually need both attributes to be the primary key of a relationship. Anyway, so the owns relationship is... Hold on. I might have made an error here. Hold on. Okay, I fixed it. So, a customer owns a car, and we can denote that relationship as customer ID and vehicle identification number. Involved in is accident ID and vehicle identification number. Insurers would be policy number and vehicle identification number. So these represent the different relationships that we have in our diagram. The primary keys for those relationships are going to be some combination of the participating entity's primary key. So one or the other, or possibly both, depending on what the mapping cardinality is. Once again, I showed both just for completeness. But once you get these 4 entities and 4 relationships, you're still not done, because we can simplify this entire set of schemas so that instead of having 8 different schemas, we only have 5. So this assumes that you went ahead and included the has relationship between customer and policy. A customer has a policy. So let's start with that. We're just going to merge that with customer. So to denote that a customer has a policy, in the customer table, we can add an extra attribute, policy number. So initially, the customer had the attributes name and customer ID. We can just merge the has relationship with the customer, and we can just use that one schema to denote that a customer has a policy number. We can apply the same logic to car. So a car is owned by a customer. We can just add the customer ID to car. So a car has the following attributes: make, model, year, vehicle identification number, customer ID, and policy ID? Well, it turns out we can play the same game with insures. So insures is a relationship between policy number and car, policy and car. We can just merge this with car to denote that a car is insured by a policy. For accident, that is, for the most part, unchanged. But we want to get the involved in schema here, because that... Okay, so previously, in class, I added the attribute cars involved as part of an attribute for accident, but it turns out the involved in relationship already has a vehicle identification number as a primary key attribute. So what we can do instead is keep the involved in relationship as its own thing alongside our other schemas. So a car is involved in an accident identified by accident ID. In class, I instead showed accident and involved in as being merged with one another, where vehicle identification number was the car's involved attribute. So that's why I have 5 attribute. That's why I have 5 schemas here for this car insurance database here. Again, it's a rather simplified database. It might be more complex in real life. That's why I allowed you to add additional attributes as needed. Additional attributes, relationships, and entities as needed. Which may also include dependents for a customer. So they would be... you would have to find some. You would have to represent dependent some way as being attached in quotes to a customer. Alright, so that is the solution for number 1 and the schemas for number 1. For number 2, here are the entities and relationships for the sports database. So I represented the 3 attributes: player, team, and match, but I also added coach just for completion, just to flesh it out further. So a player plays in a team. That's our first relationship. A team is coached by a coach, or rather a coach coaches a team. That's our second relationship. And our third relationship is match. A match is where 2 teams face off with one another. So match and team, that is a relationship where 2 teams play up against each other in a match. Let's talk about the cardinalities for these relationships. So, a player plays in a team. A player can play in one team at a time, or they may be retired, so they might not have a team ID. Or rather, they might not be in a team at all. So a player plays in a team. A coach coaches a team. A team plays up against in a match. So already we have 4 entities, 3 relationships. So plays in is many to one between multiple players and one team. Coaches is 1 to 1 between one coach and one team. It's possible that a player may be part of no team and a coach is coaching no team. Either those players or coaches are unassigned or they're retired. We can allow, for our purposes, we're going to allow that. And plays up against is a one-to-many relationship between one match and 2 teams. So 2 teams are matched up against each other, and the match table here just contains information on basically who won in that match. So, before we simplify our schemas, we're gonna need to write them out. So here are the schemas for each entity. Player has the attributes name, player ID, position, jersey number. Team has the attributes team name, team ID, and city. Coach has the attributes name and coach ID. Match has the attributes match ID, home team, opponent team, location, team score, and opponent score. For the relationships, we have plays in, where the primary key attributes are player ID and team ID. Coaches, the primary key attributes are coach ID and team ID. Plays up against, the primary key attributes for that are match ID and team ID. So we are able to do some simplification here too. So a player plays in a team, but instead of having this relationship be its own table, we can just combine the team ID attribute with the player table. So that way we implicitly describe what team the player is playing in. And if it is null, that means that player is unassigned to a team or the player has retired. We can do the same thing with team and the coach ID. So we can take this coach's relationship and just merge it into the schema for team. So team name, team ID, city, and coach ID. Now team is implicitly describing who is coaching the team. And plays up against. There are 2 ways we can go about this. The one I showed in class is where plays up against was merged with the match table here. So this is what I showed in class. I basically combined plays up against with match. So you would have the match ID, team ID. I need to put the team ID here. Actually, no. The team ID would be implied by home team In fact, home team and opponent team, those two attributes are actually team IDs. They're just renamed here. So home team would actually reference a team ID for the home team, and opponent team, the team ID for the opponent team. And then we have location, team score, and opponent score. An alternate solution would just be to not merge them, have match ID just be information about each team's score, and plays up against is information about the match ID, team ID, and whether the team is the home team. So this is just another way of representing the same information. Personally, I think it's a bit more clear with this setup because I can immediately tell who is the home team and who is the opponent team, though the information might be redundant considering each team also has a city, which could be the same thing as location, but depending on what you also include stadium information, that location could just also be a specific stadium. So this is the solution that I would personally prefer because it's a bit more clear, but it might have some other redundancies that you might find that I'm not seeing right now. Again, there's more than one way we can go about making a possible database for this. So these are the solutions for the two questions in homework 1. Questions 1 and 2 were just to make the two diagrams, and question 3 was to take one of the diagrams and turn it into a set of schemas. So if you went ahead and made schemas like these, but you did not simplify them, you were only halfway there. You would generally, in the process of turning an ER diagram into a set of schemas, you are going to have redundant schemas that you can either eliminate or merge with other schemas. And that's all there is to it. So, you do have a lab 2 whose instructions I'm going to have available on Canvas soon. And yeah, that's going to be it for this week. It's a little bit shorter because, yeah, you do have a homework and a lab 2 to work on. So I'm giving you a little bit of a break on material right now so you can then just work on the 2 assignments, okay? Alright, that's going to be it for this week. And next week we're going to continue our discussion on Chapter 4 because there is still quite a bit left in Chapter 4 to talk about. Alright,